All right, hello, welcome back to Algebra 2B. We are going to talk about special right triangles, special angles, and the unit circle. So I have a couple of right triangles drawn right here. And you could draw a right triangle with any angle between 0 and 90 degrees over here. But I've chosen some specific angles for specific reasons. So this angle is 45 degrees, meaning that this angle, because we know that the three angles, 90 plus 45 plus this, must add up to 180, this angle needs to also be 45 degrees. And on this triangle, this angle is 30 degrees, and this one is 60 degrees. So triangles with these exact proportions, these angles, are known as special right triangles, and that's because the sines and cosines of these angles have specific exact values. Before we talk about that though, let's talk about what these angles would be in radians. So I'm going to convert 45 degrees into radians. The way I convert units is I make a fraction. On the bottom, I'm going to put the units that I want to get rid of. So I have something in degrees right now. I'm going to divide by a number of degrees. And then I want to end up with radians, so on the top of the fraction, I'm going to put a number in radians. And then I want the top and bottom of the fraction to be equal to each other in their unit systems. So the equivalence I'm going to use is that 180 degrees equals pi radians. So I'm taking 45 degrees, I'm converting it to radians by dividing by a number of degrees, multiplying by a number of radians. The top and bottom of this fraction are equal to each other. Both pi radians and 180 degrees refer to halfway around a circle. So this is going to come out to be 45 pi over 180 radians. And you could get a decimal number here. In fact, why don't we do that just for fun? So 45 pi divided by 180 is this number, 0.78539. But that's not actually the answer that I want. I want to leave my answer in terms of pi. So instead of getting a decimal number from this, I'm going to try to simplify this fraction and just keep the pi there. And it turns out that 45 is 1/4 of 180. So this ends up just equaling pi over 4 radians. So 45 degrees equals pi over 4 radians, or 1/4 pi radians. They are both 1/8 of a circle or 1/4 of a half circle. Let's do the same thing here. So 30 degrees. I want to get rid of degrees. I want to end up with radians. And 180 degrees equals pi radians. This 30 divided by 180 simplifies to 1/6. So this is going to end up as pi over 6 radians. And because I have this angle 60 degrees, why don't I do that one also? 60 degrees, pi radians over 180 degrees comes out to equal 60 over 180, that's 1/3. So this is pi over 3 radians. Okay. Great. So I'm going to label all these angles on the inside with their radian angles as well. Think for a second about what a 90-degree angle would be in radians. You would do the same process. You would do 90 degrees, multiply by pi, divide by 180, and then try to simplify the part of the fraction that doesn't have pi in it. Great. Okay. So let's talk about sine and cosine. So I'm just going to call the hypotenuse of each of these triangles h. And then I'm going to try to find the side lengths of both of these in terms of h. So to do that, I'm going to use the sine and cosine of 45 degrees and 30 degrees. But instead of doing it in degree mode, I'll change to radian mode, which means that instead of typing in 45 degrees, I'll type in pi over 4. So for now, I'll just call this A and B. And I know that the sine of pi over 4 should equal A over H, because that is opposite over hypotenuse. And in my calculator, the sine of pi over 4 comes out to equal this 0.707. It turns out that this number is an irrational number, but that this long decimal is not the only way to write it. It turns out that this number is the same as the square root of 2 over 2. And this is partly why we call this a special right triangle, because when we have exactly 45 degrees, the sine of 45 degrees turns out to be exactly the square root of 2 over 2. So, square root of 2 over 2 equals A over H. That means that A would equal square root of 2 over 2 times H. These two angles are the same, meaning these two sides are the same. So we know that B should also end up being the square root of 2 over 2 times H. If we do the same process, we would need to find the cosine of 45 degrees, or the cosine of pi over 4. Because I'm in radian mode, I'm going to type pi over 4 instead of 45 degrees. And I get, indeed, this same number. So for 45 degrees, the sine and the cosine are the same number, and both legs of the triangle will have the same length. So B is also going to be square root of 2 over 2 times that hypotenuse. Okay, now let's talk about the 30, 60, 90 right triangle. So I'm going to find, I'll call this side A again, and this side B. I know that A over H needs to be the sine of pi over 6. So I'll type in the sine of pi over 6. And it turns out that the sine of pi over 6, or the sine of 30 degrees, is exactly 0.5 or 1/2. So sine of pi over 6 equals, we know that it's opposite over hypotenuse, so a over h, and that equals 1/2. So then a would need to equal 1/2 h. This one is going to be the cosine of pi over 6, or you could think of it as the sine of pi over 3. Because from the point of view of this angle, this is the adjacent side. From the point of view of this angle, this is the opposite side. The cosine of 30 and the sine of 60 are the same thing. They're the side B over the side H. Okay, so cosine pi over 6. Again, we have this long irrational number, but this one turns out to be exactly equal to the square root of 3 over 2. You can see that those are exactly equal. So that means that B would equal the square root of 3 over 2 times whatever the length of the hypotenuse is. Great. So now we found the sides of both of these triangles in terms of h, and we also practiced converting to radians, and we ended up with these square root numbers. Now I'm going to take these angles and put them in the context of the unit circle. So this right here is 30 degrees. This middle one is 45 degrees. And this one is at an angle of 60 degrees, measured counterclockwise from the positive x-axis. That's always how we measure angles. So, because this is the unit circle, we're saying that the hypotenuse is exactly 1, which means that the side opposite of 30 degrees must have a length of exactly 1/2. And this bottom side, the angle, or the side adjacent to 30 degrees, must have a length of exactly square root of 3 over 2. So the coordinates of this point would be the square root of 3 over 2 times the hypotenuse, but that's 1. So the x-coordinate here is this adjacent side to the 30 degrees. It's just square root of 3 over 2. And the y-coordinate is 1/2. 45 degrees, the x-coordinate is the square root of 2 over 2. The y-coordinate is also the square root of 2 over 2. And 60 degrees, it should make sense that the x and y coordinate of this one are just going to be flipped around. In this triangle, the side that is adjacent to 30 is opposite of 60. The side that's adjacent to 60 is opposite of 30. So between 60 degrees and 30 degrees, the sines and cosines are just switched. Or if you want, you could think about this 30-degree angle and realize that the side opposite of 30 is 1/2 times the hypotenuse, and the side adjacent to 30 is square root of 3 over 2 times the hypotenuse. There we go. Let's also add the coordinates of these 2 points. The x-coordinate here is 1, the y-coordinate is 0. The x-coordinate here is 0. The y-coordinate here is 1. If I told you to draw me a right triangle where two of the angles are 90 degrees, that wouldn't really make sense. So these numbers don't really make that much sense in the context of a triangle. But remember, in the last video, we talked about how instead of using triangles to define what the sine and cosine of an angle is, we're just going to use the unit circle and define the sine and cosine as the coordinates on the unit circle. So this point is 90 degrees away from the positive x-axis going clockwise or counterclockwise. Its x-coordinate is 0 and its y-coordinate is 1. So what that means is the cosine of 90 degrees equals 0, and the sine of 90 degrees equals 1. Even though we couldn't really draw a triangle with 0 degrees or with 90 degrees, these angles still have a sine and cosine based on the coordinates. Okay, this is a lot of tricky numbers to remember, so I'm going to teach you a way to try to keep track. So I'm going to start with the sines, the y-coordinates, and I just have these little lines here representing each of the points we just talked about. Or you can even kind of put your hand here and count it on your fingers, where this one represents 0, 30, 45, 60, and 90. So I'm just going to start at the positive x-axis like I usually do, and I'm going to count the lines starting from 0. 0, 1, 2, 3, and 4. Now, each number gets a square root and then gets divided by 2. So I have 0, 1, 2, 3, 4. I did the same thing to each of these numbers. And now some of these things can be simplified. Square root of 0 is just 0. Dividing 0 by 2 is still 0. So this just equals 0. The square root of 1 is just 1. So this equals 1/2. This one doesn't simplify. This one doesn't simplify. And then the square root of 4 is 2. So that makes 2 over 2, which equals 1. So this is an easy way to remember what the sine of each of these angles is. 0, 1/2, square root of 2 over 2, square root of 3 over 2, and then 1. You can just count from 0 up to 4, and then you have to remember that you're supposed to do the square root and divide by 2 for each one. And like we said, the sine and cosine are basically just switched around. So I start with 0 down here. For cosine, I go 0, 1/2. The next one is square root 2 over 2, square root 3 over 2, and lastly, 1. So this is an easy way, maybe it'll take a little bit of practice, but to remember the sines and cosines of all these angles between 0 and 90 degrees. We count up, going this direction for the sine, we count up going this direction for the cosine. Every number gets a square root, and every number gets divided by 2. Okay. think I'm gonna stop it there and record a second video on solving problems on the unit circle using these special right triangle angles.